Okay, so what I want to talk about today is how to solve optimization problems. Solving optimization problems. That means problems of the type when you are given a function g and your task is to minimize the g over some set. And that's motivated by what we did the last time when we converted the implicit Euler into exactly this type of problem, into an optimization problem. And I told you that in practice, that's the best way to go about it. That's the best way to solve this. So maybe I figured out today how to do a recap without actually just repeating what I said before. So the way I would like to do the warm-up today is by showing you how to do the optimization formulation of implicit Newmark. Okay, so let's go through that. Implicit Newmark. What we did last time was we did this for backward or implicit Euler. And what I'd like to show you is the same derivation for Newmark, which is a different integrator, of course, with entirely different properties than backward Euler. But it turns out that the resulting optimization problem is almost the same, which is kind of motivation why it makes sense to talk about optimization problems in general. So let's take a look at implicit Newmark. So we have these two update rules, which you should probably remember by now. So that's the update of positions using our usual conventions, and the update of velocities, Vn plus h half, and now we have the two forces. That's how it's different from backward Euler. Xn plus 1, as usual, f are forces, right? So we have the first update rule, the second update rule. So as before, the first trick I will put these things together, right? Because the first equation is linear, so I can essentially deal with it and convert it to just a single equation. So the way I will do it, so from 1, I will express what is h half Vn plus 1, okay? And that will be, I just put this on one hand side, xn plus 1 minus xn minus h half of Vn. Okay, so I just isolated this term Vn plus 1 from the first equation, okay? You can write it like this if you will. Now what I can do, I can multiply the second equation by h half, right? So I get the same thing on the left-hand side. It's kind of simple, plus h squared divided by 4, and now f of xn plus f of xn plus 1. All right, so I just took equation number 2 and multiply both sides by h half. H is the time step, as you know. All right, so now I can put both of these things together, right, because the left-hand side is exactly the same. And what I'll see is that xn plus 1 minus xn minus h half Vn equals, let me do baby steps here, h half Vn plus h squared over 4. And here is fxn plus f of xn plus 1. All right. So I can put this together, right? So I can, or simplify this slightly. So this becomes just minus xn minus hvn, right? Because I can put this guy to the other side. And here it remains h squared fourth, and the same thing, fxn plus fxn plus 1, okay? And if you remember what we did before, we said let's simplify the notation a little bit. Let's introduce the symbol y, which by definition is xn plus hvn, right? We talked about the physical interpretation of this term the last time. Do you guys still remember it? Hmm?
Like Newton's first.
Exactly. Newton's first law. Motion without the presence of forces. Very simple thing, yeah. All right, Abhishek. So that's the y. And also I will, instead of xn plus 1, I will just write x. Okay, so I'll simplify this formula to x minus y equals h squared. Oh, you know what? I can actually make it even slightly better because this term is constant too, right? So I can actually make it even slightly simpler. So I can put this on the left-hand side, h squared fourth f of xn. Those are the subtle nuances from the backward Euler, okay? H squared fourth of fxn plus 1. And now guess what? I can say that this entire thing is my y, okay? So nothing prevents me for dropping this term h squared fourth of f of xn. Let's say that this is now my y, okay? The point of the y is to just group the terms that are constant, right? I already know what xn is, I know what vn is, I can certainly compute f of xn, so I can compute this, and it's just gonna be a constant as long as this integrator step is concerned, okay? So if I do this and instead of xn plus 1, I will just write x, then I can write this as x minus y equals h squared fourth of f of x, okay? Or equivalently, x minus y minus h squared fourth f of x equals 0, right? Which I can also write as x minus y plus h squared fourth, the gradient of the potential at x, okay? And as we discussed the last time, this corresponds to a function g of x, where g of x is 1/2 of x minus y squared plus h squared fourth of e of x. Okay, and the way it corresponds is this way. Then the gradient of g of x is 0 if and only if this formula is satisfied, right? Because the gradient of this is exactly that. So if I set it to 0, I'm exactly where I started, okay? So now, if this E is convex or almost convex, this first term is always convex, right? That's what we said the last time. It's a quadratic convex term. It doesn't get any easier than that. Then solving this system of equations, which can be nonlinear, is equivalent to minimizing the function g. Okay, so our problem is an unconstrained minimization problem. Take this g function, given some initial guess, and we want to minimize it. Okay. If the function is convex, then the minimization exactly means that if we find a point, a critical point, that point needs to be actually a global minimum. I will talk more about that in a second, okay? So so once I solve this optimization problem, which sometimes you can write this in a fancier way, you might see this in some papers, you can see this as argmin, and then I can say that xn plus 1 equals the argmin. The argmin means give me the x that minimizes that function, okay? And then I say my time step, my result is gonna be exactly this argmin, okay? That's what I mean by this. And once I've computed xn plus 1, it's an easy matter of computing vn plus 1, right? Because that's just from the rule number 1. And I get that vn plus 1 is 2 over h times xn plus 1 minus xn minus h half vn, okay? That's just isolating the vn plus 1 term from the update rule number 1. So that's the easy part, the velocity update. The hard part is actually solving this optimization problem, okay? And notice, if you remember what we talked about before, for backward Euler, the optimization problem we got was almost the same. Almost. What were the differences? Do you remember? So this optimization problem, this G, corresponds to implicit Newmark. In the last lecture, we had the G that was corresponding to backward Euler, right? And they were kind of similar, but not exactly the similar. There are some subtle differences. The one subtle difference is this y, right? Now we have this term that was not there in backward Euler. And the other one is this divide by 4. We also did not have that in backward Euler, okay? So that's all how the integrators differ when converted to an optimization problem. And by the way, many other integrators you can also convert to an optimization problem, such as midpoint, and that's usually the best way to solve this. So now let's talk in general, if everything is cool here. So what I like to do next is to talk in general how to solve a general optimization problems of this form, okay? Which is something, so the problem is, so the problem is, I will have a function g. It can be a multivariate function, so it can be a function from Rn to R. Sometimes it's called objective function or cost function in this context of optimization. And my goal is to just minimize it, okay, over x from Rn. Usually you assume that g is like twice continuously differentiable or something like this. Basically, the g needs to be nice enough so you can minimize it. And the minimization is much more general than physics-based animation. It's important in physics-based animation, but it's used in lots of other areas too. In machine learning, it's used a lot. In statistics, I guess pretty much everywhere. Whenever you have some numerical problem, you can usually convert it to an optimization problem. And then you can use these tricks from optimization to solve it efficiently, okay? So the first thing I would like to do is to give you like at least a crude overview of what optimization methods are there. There's an entire zoo of optimization methods, and I would like to give you at least a very brief overview. Did you have this in some? Did you heard about things like convex programming, linear programming, quadratic programming? Oh, it's usually called programming, by the way, which is the historical term how people used to refer to optimization before, like programming. Now the modern term for program is coding, right? But people historically, instead of optimization, were saying programming. So when you hear things like linear programming, quadratic programming, convex programming, constraint programming, and all sorts of versions of this, that refers to optimization problems. So the first, I guess, the simplest case, unconstrained versus constrained optimization problems. So the constraint would mean that you are not allowed to pick any x from Rn, but you have some constraints, okay? And those can be equality constraints of the form Cx equals 0, or you can also have inequality constraints. Some function dx has to be greater or equal than 0, okay? And these things define what's called a feasible set. Okay, so we say that x is feasible if it satisfies all these equality and inequality constraints, and then the name of the game is to minimize the gx such that these constraints are satisfied. That would be called constraint optimization. Okay, this is sometimes useful in phys-based. It's good to do like these attachment constraints, like for example for these kinematically controlled vertices, even though in that case you can do it in an easier way, because if these equalities are not too complicated, you can just directly eliminate it from the g function. Okay, and convert it trivially to an unconstrained problem. Okay, but when we start talking about collisions, now the inequality constraints become important because, for example, if you have some ground, right, and you want to say that some particle cannot go beyond ground, the most natural way to express this is an inequality constraint. Okay. But nevertheless, the most important case is unconstrained optimization, also because the constraint is just like a special case of that. So we'll mostly talk about unconstrained methods here. There is a special class on optimization if you want to go into that more. I think Dimit took it last semester. How was it called?
The intro optimization.
Yeah. Is it the CS or is it math?
It was the math.
Oh, okay, it's a math department class, yes. And there you learn all this theory, and you hear things like Lagrange multipliers or KKT conditions. That all belongs to the constraint optimization. Okay, so I won't go too much into that. Now there is another division which is actually even more important. There is a division between convex and non-convex optimization. And that is very important. So I guess first I need to show what is a convex optimization problem, right? So first, the g function must be convex. The function we are minimizing, we are convex. And if we have a constraint optimization case, then the feasible set must be also convex. Okay? So do you all know what it means for a function to be convex and for a set to be convex? James?
So for a function or a set to be convex, if you draw a line between any 2 points on your curve, it's within your region, within the curve.
Yeah, that's exactly this idea. And this, you're right, James, and that directly extends also to multivariate functions, right? Because in general, you go from Rn. So this picture might be multidimensional. So if you want to write it in a formula, then you will say that for each x1 and x2 from your domain, and I will just skip the domain thing, and for every t between 0 and 1, you have the following inequality. You can say that the g function evaluated at a linear blend between x1 and and x2, those are the two arbitrary points, needs to be below the linear blend of the values, okay, which means this, plus t g of x2, all right? And that's exactly this picture you had on mind. That's the picture to have on mind, and this is the corresponding formula, right? Because this value is the g of x1, this value is the g of x2, and this says this is for t equals 0, right? This is for t equals 1, and this says that if I blend, if I take t, I don't know, 0.3, right, and I evaluate the function g, this is the g function, right? If I evaluate the function g and I evaluate a linear blend between gx1 and gx2, then this guy needs to be above, okay? Which is a way to say that this function is sort of like a bowl shaped. And this works in arbitrary dimension, okay? So that's convexity of a function. And a similar condition works for convexity of a set, right? So if I have some, let's say I have some set omega, and we say that it's convex when, what is it for a set? So set is not a function, right? That's some sort of collection of things. You can draw the set like something like this.
Wouldn't it mean that similarly with any 2 points, the line drawn is maintained inside of the set?
Exactly. Yeah, exactly, Brian. And that's again the good graphical picture to have in mind, right? So you can see that this set won't be convex because I can pick these 2 points and the entire line is not gonna be in the set. But if I pick some shape like this, then it's gonna be true, right? Whatever 2 points I pick, then the entire line is inside, okay? So I guess there's no need to even write the definition. It's kind of obvious now, right? Yeah. Oh, there's no inequality. Maybe I'll write it just to be complete. So for every x1 and x2 in omega, it's similar but not exactly the same. So now the linear blend between x1 and x2 is in the set. So there is no inequality now. All right, so an optimization problem will be called convex if both the function is convex and the feasible set is convex, okay? If anything of this is violated, if either G is non-convex or the feasible set is non-convex, then we talk about non-convex optimization, okay? There's one subtle detail. If G actually was concave, what means concave? Concave means that minus G would be convex, okay? That's exactly the opposite picture, okay? No, if you are minimizing a concave function, it would still be complicated. If you are maximizing a concave function, but I guess that's not what I wanted to say. Oh yeah, the one thing I wanted to mention, the convexity of a function you can equivalently test by looking at its Hessian of the function, and that the Hessian is positive semi-definite at every point. Then that's equivalent to saying that the function is convex. So when you have a constrained optimization, then it's very easy to run into non-convex problems, okay? Like for example, if you have a single equality constraint, okay, and the equality constraints looks like this, it says that the x needs to stay on a unit circle, okay, so I would say that I would say like this, norm of x equals 1, okay, then the optimization problem is convex or non-convex. If the unit circle is my domain, that's my feasible set. It's not convex. if it's just the circle, then it's not convex, right? Because if I actually almost any 2 points I pick, the line goes immediately outside. Now the trick is if it was like this, if it was the circle with it inside, then it would be convex. Okay. So I guess what I want you to remember is as soon as you have even a single nonlinear equality constraint, it immediately becomes a non-convex problem. Yep.
What about just a square? Would the square be convex? It's like if you take 2 corner points, would the line that is the border be within the set as well?
So again, depends whether you are talking just about the boundary or the entire interior. So if you're talking just about the boundary, then you immediately have a counterexample, right? So some of them will work out, but once you include the interior, then it becomes convex, right?
But are 2 points on the same edge valid then?
Oh, that's not enough, right? It needs to be true for any 2 points in the set, right?
So let's take the case of less than equal to 1, so the full square, with 2 points on the edge.
Sorry, I don't follow.
So if
Do you
you
want to?
take the second example where
Yep.
norm of x is less than or equal to 1, or just within the unit square,
Mm-hmm.
I guess that would be the first one. But and if you take 2 points on the edge, does that still satisfy the conditions of a convex set?
Okay, so we are talking about the inside of a circle. I don't know what you mean by 2 points on the edge.
So in a square, if we go back to the square.
Oh, okay, sure.
And we pick 2 points on the left side.
Like this?
Yes. Is that valid?
I think so.
And you are talking about with the interior or just the boundary?
The interior.
So with the interior including the boundary,
Yes.
then that's fine.
Okay.
Now there's a subtlety, and I don't really want to get into that, like whether the boundary is there or it's not. That's like in calculus, that's called open versus closed sets. And it actually does not matter. And those are like really like nuances of calculus. Like when we are solving actual problems, kind of whether it's like less than or equal or just less, that kind of in practice doesn't really matter because eventually you have a finite precision arithmetics anyway, right? So.
Okay.
Yep. All right, so the reason why it's important, the distinction between convex and non-convex is that the theory for convex programming, convex optimization, is very well worked out, okay? And when the problem is convex, it's generally easier to solve, even though not always, okay? And there are certain special cases of convex optimization. For example, if the g is linear, if the objective function is linear, and you have linear equality and inequality constraints, then that case has a name. That's exactly linear programming. So that's a special subspecial type of convex optimization. You might have heard the term linear programming because that's one of the best studied cases in optimization since like many decades ago. Now, when you have also linear equality and inequality constraints, and the G is quadratic, and this becomes the same, you might have heard this term too, then it's called quadratic programming. And I want to, on the quadratic programming case, I want to illustrate why the convexity of G is important, okay? Because if G quadratic doesn't tell you whether it's convex or non-convex, right? Quadratic functions can be either convex or non-convex, okay? And here in the quadratic programming, there is actually a huge difference. If the G is a convex quadratic function, then it's a convex QP, convex quadratic program. This is sometimes called just QP and linear program just LP. So when we have a convex QP, then there are very reliable polynomial time algorithms, okay? So that's a polynomial time. It's not exactly easy to solve it. What you would probably want to do is to use some existing solvers, such as Mosaic is a very high quality commercial solver, but then you can basically consider it done, okay? Whenever you have an optimization problem and you found that it's a convex quadratic program, you don't want to be writing a solver by yourself. You want to just call an existing solver, okay? That's actually true for any convex optimization problem. It doesn't necessarily have to be QP, but QPs, they appear quite frequently in practice. Now, what happens if it's still a quadratic program, but it's a non-convex one, okay? The non-convexity can come only from the fact that the G, the quadratic function, will be non-convex, okay? For example, it could be concave, right? Like this. Okay, you still want to be minimizing it. And actually, in this case, you can prove that this is NP-hard. Okay, so there's a huge difference between the convexity and non-convexity. Now, that said, not all non-convex problems are equally hard. Okay, the set of non-convex problems is incredibly vast. And basically, I can tell you the intuitive reason why this becomes NP hard, and that's basically the curse of non-convex problems. Okay, so if you have a non-convex function, then the non-convex function can look something like this, and that's just in one dimension. Imagine it as multiple dimensions, right? So what the problem is that this function has lots of local minima, and all the current optimization, or most of the optimization techniques, are just prone to getting stuck at a local minimum. Okay. In the convex case, of course, this cannot happen, right? Because in the convex case, a local minimum is global minimum too, right? That's kind of the main difference between convex and non-convex problems. Now, but what I wanted to say is that not all non-convex problems are equally hard. It's not always this like nightmare kind of scenario. It's sometimes the non-convexity is kind of benign, kind of like this, okay? And this kind of turns out to be the case of the problems we are usually solving in phys-based animation. Okay, so they are technically speaking non-convex, but they are not like evil like this non-convex QP, which would actually be NP hard. Okay, so it doesn't mean automatically that you should immediately start panicking if your problem is non-convex. I'll actually give you some examples to further drive this point home. Some non-convex problems can actually be solved efficiently. I'll give you a trivial example, and then I'll give you a less trivial example. It nicely connects to what you might know from linear algebra. Okay, so think about this problem. I give you a problem: minimize the norm of d minus x. Okay, a standard Euclidean norm. D and x are R3 vectors, no constraints. Okay, just minimize it over. Oh, sorry, there is a constraint. I want to say that the norm of x equals 1. Okay. So let me go over it again. So D is a given vector. I give you a D. Okay. I want you to find an x such that the norm of x is 1 and the Euclidean norm of D minus x is minimized. It doesn't matter if it's a 3D or 2D or ND vector, by the way, but just to make it concrete, I give it a 3D. Now, can you tell me just intuitively what the solution will probably be? And once you get it, then it will probably be the correct solution.
I don't know, I might be off, but is it just when the x is pointing in the opposite direction? D?
So yeah, you're on the right track. So D is a vector, right? That's my D, right? Mm-hmm. It's an arbitrary vector. I didn't tell you anything about the D vector, right? Hmm?
Oh yeah, in the same direction.
In the same direction. That's right. And so yeah, I agree. X should be pointing in the same direction as D. And norm 1, right? So what is the formula?
I don't understand the minimization function.
Oh, that's
the minimum of the value, the absolute value of x equals 1. What does that mean?
Oh, that means the Euclidean norm of x is 1. So that means I could also write it like this, right? X, or like, if I'm in 3D, I can write it also like this. Square root of x1 squared plus x2 squared plus x3 squared equals 1. That's what I meant by that.
Oh, okay.
This is my notation.
Normally, like I think of minimization, you're minimizing over like the range of a variable.
You don't have to. This is an equality constraint, right? This is a perfectly valid equality constraint. Equality constraint is a function.
I was trying to figure out what the notation means.
Okay, that's a great point. Let's talk about it. What does that mean, actually? What does this constraint mean? I guess I was trying to be a little too fast, but I think I should have explained that properly. So what is this constraint geometrically? The norm of x equals 1. So if I was to write it properly, what I'm talking about is a feasible set of vectors from R3 such that the Euclidean norm of the vectors is 1. Okay? How does this set look like? Yes, the surface of a sphere. The interior is not there, right? From this, you immediately see the problem is non-convex.
So we're minimizing this function, but only where the answers are on the surface of the sphere.
Exactly.
Okay.
It's a constraint optimization problem, that's right. Sorry, I think I went over it a little too fast. This is the objective function, this is the cost function. We want to make this as small as possible, but we have to satisfy this equality constraint. Okay, this one, the equality constraint is not negotiable. Okay, if that is not satisfied, your solution is wrong, no matter how good the value of the objective is. Okay, that's the contract of constraint optimization.
So that's a constraint function and the cost function.
Yeah, if I was to put it in the notation I had there before, I would say that my constraint function looks like this, right? That's it's a single nonlinear equality constraint. I could put it like this, norm of x minus 1, right? And then it exactly fits this. Then the cx equals 0 is exactly what I wanted. Sorry, I think I really went over a little too fast. I'm trying to cover too much ground today. All right. So, okay, so again, I gave you a d vector, arbitrary d vector. That's your input, okay? And your job is to find an x which lies on the unit's sphere and minimizes this objective. How do you think such an x will look like? Exactly, yes. So the solution, which in the context of optimization usually write like x star, will be d divided by the norm of d, okay? It really means just projecting the d onto unit length, right? Because if you think about it geometrically, you have a unit sphere, right? You want to you need to return some vector on the unit sphere, right? But you want the one that is closest to d, so clearly that's gonna be this one. Okay, this is not a proof, but doing a proof is not too hard. Just need to do a little bit of math. So what this example illustrates that even though you have a non-convex problem, the solution does not have to be difficult. Okay. I will show you one more. This was the trivial example. I will show you a non-trivial example. Okay. Let's take a look at this. I want to minimize a half of ax squared, subject to the constraint, which is actually the same, that norm of x is 1. Okay. So now my A is an M by N matrix. X is an Rn vector. Okay. The constraint is kind of the same as before, except that now it's in n dimensions. So it's like an n-dimensional hypersphere, if you unit hypersphere or whatever you want to call it. But the funny thing is that now I have a matrix here, and I'm minimizing the square norm of ax. Okay. So first things first, right? Clearly non-convex problem immediately, right? You have, you have a single but in nonlinear equality constraint immediately non-convex, just like in this case, okay? And it turns out that this problem still has a polynomial time solution. Does anybody know what that is? Yeah, you are absolutely right, British. That's exactly what that is. So the solution, the x star is eigenvector of A corresponding to the smallest eigenvalue. Of what? There's a little detail there. Of ATA. Right, because this matrix is not even square. ATA is always square, symmetric, therefore it has a full set of real eigenvalues. I can certainly find the smallest one. I can find the corresponding eigenvector in polynomial time, n cubed, right? Or n squared m or something like this. It is definitely polynomial time, and that's the solution. If you want to prove that that's the solution, you can do that for a homework, and the hint is Lagrange multipliers. By the way, if I wanted to maximize this, then the solution would be the eigenvector corresponding to the largest eigenvalue of ATA. Okay, which, by the way, this thing, I think, is one explanation why the eigenvalues and eigenvectors are so important. This is like an optimization perspective on it, because it really gives you a solution to a complicated non-convex problem. So this is actually a class of non-convex problems that we can solve very efficiently. These examples are very rare. There is not too many non-convex problems which we can solve efficiently, but these are some of them. Yep. Oh yes, that's a great point. The solution does not have to be unique. That's also like a contract in general optimization. So when I ask you to minimize this gx, or even better, if I tell you, I ask you to give me an argument of gx, okay, and it can be constrained or unconstrained, that doesn't matter. Usually the contract is, that means give me a solution, okay? And if I'm talking about a global optimum, that just means that there cannot be a point that would be feasible and would have lower value of g, okay? That doesn't mean there is a single point that has this property, okay? That's the case even in convex optimization, right? Sometimes you can have many points which all of them would be valid global optima, okay? That's entirely possible, okay? In which case, usually the contract is give me one of them, and that's good enough. Yes, so Reddish is completely right that, of course, this would not have to be unique, right? Depending on the spectrum of ATA, it could have a bunch of eigenvalues that would all be 0, so that each of the corresponding eigenvectors would be equally valid solution. You cannot say that one is better than the other. And usually you don't worry about finding all of them. Usually just one of them is fine, because after all, they are all equally good. All right, so I could keep going from now and just go talk about convex optimization for the rest of the semester, but I won't do that because there is this class in math that does exactly this. I will just give you, in case you don't take the class, I will just give you like the street fighting tips. So if you have convex optimization, don't try to write your own solver. Use an existing solver, okay? Convex optimization is very well studied, and the convex solvers usually work fairly well. In the case of constraints, those would be interior point methods. And there is, if you just Google it, you will find a ton of solvers. There is the CVX from Stanford. Each of them has like a little bit different flavor. There is Mosaic that has a large collection of convex tools. There's Burabi and some semi-definite programming methods. Those are all different flavors of convex solvers, okay? Now for non-convex, non-convex is slightly trickier. Solvers also exist. High-quality solvers have been developed for non-convex optimization, and actually they use pretty much the same ideas as the convex ones, okay? The difference being that you don't have any guarantee that you'll find a global optimum with a non-convex solver. You are usually only guaranteed you will find a local optimum, okay? So if you have a situation like this, then usually you cannot expect you will find the global optimum here. Usually any of these points will be as good as you can expect, okay? But even finding this local optima is sometimes useful and not easy. And what the non-convex optimization essentially boils down to is using the ideas from convex optimization with some further precautions, okay? And that actually turns out to be exactly the case we have to go through in physics-based animation, because in that case we are in this kind of regime when it's like slightly non-convex, but we need to make the code robust so it just does not crash in case it just happens to be around this little concave bump, okay? Now there are some nice solvers like IPOpt or a commercial version of it, Knitro. They usually work like this, that you have to give it a code for the function g, and the solvers are most happy if you also give it the code for derivatives, the gradient of g, and also the Hessian of g, okay? So whenever possible, give it the gradient and Hessian, and you can expect these solvers to be more happy. And what that means for you is that they will take fewer iterations, usually, okay? The non-convex solvers are a little bit more finicky. They have some parameters which need to be tuned carefully, otherwise they might not work so well. So it's less robust than the convex optimization case, where you can even prove that these algorithms are polynomial and the tuning of the parameters is less complicated. But yeah, if this is the best you can do, then you can just use some of these solvers and see how that goes. Now, for special cases of problems, that's the thing, that not all non-convex problems are equal, right? We have seen some non-convex problems like these guys, which can be solved very well in polynomial time. Then there are some non-convex problems which are not so hard to solve, like the typical implicit integrator updates. And there are some non-convex problems which can be NP hard. So there's an entire spectrum out there, okay? So the right thing to do if you really care about having a really good solver, like in FizzBase 2care, because you will be running the implicit integrator over and over and over and over again for many steps, then it actually pays off to look into the specific structure of your problem and see if you can come up with some nice customized solver for that. And that's kind of what I would like to do now. I would like to explain you some basics of optimization. Just the very basics. We'll just talk about the unconstrained case. And we'll talk about the optimization problems that corresponds to solving implicit integrators, okay? Because it turns out that if you just want to solve implicit integrators of backward Euler or the Newmark one, that using these packages is kind of an overkill because you can code it up yourselves if you know few tricks of the trade, which I would like to tell you now. So there is just few tricks you need to know to get a nice solver that can handle even this mild non-convexity, okay? And we'll talk just about the unconstrained case. The constrained case is slightly trickier, not too much, but I want to go too deep into optimization. So there are two main classes of optimization methods used both in the convex case as well as the non-convex case with extra precautions. You might have heard about descent methods. And then there are trust region methods. And they are actually not terribly different, okay? And the descent methods are the easier case, the easier ones of them. And for the problems in FizzBase, they are typically sufficient. We had pretty good experience with them. So I'll talk about general descent methods. And also unconstrained. So no constraints. Even in this case, there are a few tricks which are good to know, okay? So the idea of all descent methods is that we will iterate and we'll iteratively get to the solution. So we'll start from some x0, which is our initial guess. Almost all of these algorithms require some initial guess. That's true even for the convex ones, where the initial guess is less important because the solution is better defined, because you don't have the local global minima problem. But good initial guess can get long ways in getting you a good result. By the way, what do you think would be in the good initial guess for the Newmark problem, the implicit Newmark integrator problem? And we are minimizing this objective, right? Every solver will require you to provide some initial guess. If you have like a library, sometimes it can produce a guess for you, but it won't be particularly intelligent. It could be like all zeros or something like this. So if you can come up with a more educated guess, you might expect it will work better. What would be your first guess? You can always start with x equals 0, right? No problem. But especially in the non-convex case, it's a little more sensitive to the guess. Yeah, just y, right? Start from the y. That's kind of nice because it eliminates the first term entirely, and that becomes 0, right? And then you essentially just like, then you depart from it, then you increase this and trade it off for decreasing this. That's kind of the idea. So you're exactly right, Junior. Starting with x0 equals y is the usual initial guess we would be using in these kind of problems. All right. But let's talk in general about the descent method. So we give it some initial guess, and then the idea is to generate a sequence xk, meaning x1, x2, and so on, okay, such that you are always decreasing your objective, such that the g of x2 will be strictly less than g of x1. This will be strictly less than your value at the initial guess, okay, and so on. And at some point you say it's good enough, and you just return the xk as the solution, okay. So so all of the descent methods, and there's a lot of them, they have the same structure. So the pseudocode could be written like this. You start with k equals 0, and then you have a loop, repeat. The first step is to pick descent direction. And I will call that d. Okay, that will be an n-dimensional vector if our function is n-dimensional, the cost function. Now the second step is line search. And that means pick step size alpha greater than 0, okay? Number 3 is do the step, so meaning compute xk plus 1 simply as an assignment, and that's xk plus alpha d, okay? And increase your k plus plus. And you repeat this until converged. All right, so this is the skeleton. This is the, I guess, 10,000 feet view of any descent method. So these are some comments. So first, the descent means that you are doing a sequence of line searches. You essentially convert the multivariate optimization problem into a sequence of one-dimensional optimization problems, okay? So meaning you start somewhere at some point, and you pick some direction, and you will say, let's try to minimize the function in this direction, okay? That's exactly what the line search does. It tries to find an alpha such that after you do this step xk plus alpha d, so the alpha is a scalar, positive scalar, the d is the direction. After you do this update, then hopefully the objective value at xk plus 1 will be much smaller than the one at xk. Okay, I could write the hope, or the invariant is that the g of xk plus 1 must be strictly less than g of xk, and the hope is that it will be significantly less. Okay? And there is some stopping criterion when you say, this means there is some stopping criterion which says at what point you are already happy and you stop iterating. Okay? What do you think would be some reasonable stopping criteria? Yeah, that's actually the easiest one. Just give it a certain number of iterations, right? The problem with that is you don't know how good quality a solution you are getting, right? James?
You could have some percentage of the initial value g.
Uh-huh.
If you start with x, and then it's converging until it's only 10% of x, you decide you have diminishing returns and stop.
Exactly, yeah. So that's kind of like the concept of a relative error, which is actually very, very useful. Brian, you had something?
I was thinking absolute error. So give it a certain threshold distance. If you know the scope of your equation, you can determine what value is precise enough. So same thing, but just more absolute.
That's a good idea. And usually you would like to impose it not directly on the function, but on the gradient of the function. Okay, so if the gradient of your function at xk plus 1 is small enough, where this epsilon is some threshold, then you can say we stop, right? Why the gradient? Because why the gradient? You tell me.
Because it's the rate of change.
Exactly, yeah, because you don't know where the minimum is gonna be, right? The minimum can be at like 2 millions, right? And that can be the smallest possible point. But you know that when you are at if it's a convex problem, you know that when you are at the minimum, that the gradient has to be there 0, right? The gradient can be also 0 at a critical point, at like a saddle point, but it's kind of unusual to converge to a saddle point with an optimization method.
So
Yep.
on this line, I have another question. So what if we pick the wrong direction and we're not going to find any line in that direction?
Correct. That's why I said the descent. Okay, and that's the next thing I want to talk about. What does it mean to have a descent direction? So not every direction is good, of course. And actually not even every descent direction is good, but that will be the topic for subsequent discussion. So that's a great question, because that's the thing I was going to talk about next, if I understood you correctly, right? Basically, for what is a descent direction, first of all, right? I didn't even define that, right? So descent direction, that means... So that means that there exists some small epsilon. Okay, let's get rid of this epsilon. This is a different epsilon, just some small positive number, such that for each alpha between 0 and epsilon, the function actually goes down, okay, in that direction. So fx plus alpha d is strictly less than f of x. So that kind of intuitively makes sense, right? If I make a sufficiently small steps in the descent direction, then my function is actually getting lower. Sorry, I'm not sure why I put f there, because I meant to write g. I don't want you to confuse it with the forces. That's why I write g there. It's nothing to do with the forces. Oh, and by the way, this alpha has nothing to do with the step size. This alpha has nothing to do with the time step. Okay, it's a kind of step, but it's a step of solving the optimization problem. Okay, it doesn't have anything to do with the time step, and we are solving integration. Okay, even though people use the same word step, so don't get confused. Confusingly enough, in some literature, this will be also like denoted as t or something like this. So it kind of might look like a time step, but it's not a time step. Okay. When we are doing this iteration, you are not integrating anything, or just solving an optimization problem. Okay. Once you are done, then you might have solved an integrator, fine, but that's a different story. Okay. So this is the definition of what a descent direction is, but this is not very useful for determining what directions are actually descent directions, but it's actually not so hard to think about good descent directions. And to think about good descent directions, it's kind of intertwined with the problem of what the line search is, right? So let me talk about the descent direction needs to work well in line search, right? So line search means, ideal line search would give me this. It would minimize this function, okay, over alpha is a positive scalar. And ideally, I would return the alpha such that the fx plus alpha d is as small as possible. That's really the idea of a descent method. It converts the problem into a sequence of one-dimensional optimization problems, okay? So the line search, you can, so now this is a 1D optimization problem, right? So if it's a convex case like this, that's a 1D problem. So the optimum is here, okay? Does that make sense? Once you have picked a descent direction, you are down to a one-dimensional optimization problem. So we are at a point, we pick a direction, and we'll say how far in this direction I should go to minimize my function as much as possible, okay? And that, of course, amounts to minimizing just this function, and that's a function of a single scalar parameter. So I can call this function phi. It's a function of alpha, and it's a function that looks exactly like this. It's x plus alpha d. If you want, I can put their little vectors to make it clear that the x and d's are vectors, whereas alpha is a scalar, and it's also a positive scalar, okay? So really, what I'm doing, I'm minimizing this function phi of alpha, okay? And here is an interesting thing about the function phi of alpha that helps us understand what are actually descent directions. So let's take the derivative of phi at 0, okay? So first of all, let's take the derivative at any point. What is the derivative? Well, I just apply the chain rule, right? So that will be f of x plus alpha d gradient transpose times d, okay? That's just multivariate chain rule as before. And now the phi derivative at 0, the 0, that's where I am at, right? If alpha equals 0, that means I'm at x, and that's my current iterate. Okay, that's my current iterate xk. I kind of assume that this I start with the initial guess, k is 0, so now here I am at xk, where I'm picking the descent direction. Okay, so I need to pick a good descent direction such that when I go from xk, as it's written here, I will get nicely down. Okay, so the f derivative at 0, I just plug for alpha 0, right? So I'll just get the gradient of f of x transpose d. Okay? Now, on the other hand, I can also write this differently, right? I can, let me do it like this. How should I do it? Grab this over here. On the other hand, you know how a derivative is defined, right? You know that derivative is the limit of the function, in this case fx plus alpha d, minus the function at 0, so that's f of x divided by alpha, where alpha goes from the right to 0. Okay, it's just like a little bit of a calculus, but it's not that hard. Right, and now what I claim is that if this derivative, so if this thing, which is exactly derivative of phi prime at 0, if this is negative, okay, so let's assume, that's what this if means, that this is negative, then I also know from calculus that there exists some epsilon such that for each alpha between 0 and epsilon, I probably should have written epsilon greater than 0, it will be true that this whole thing needs to be negative. Okay, so fx plus alpha d minus f of x divided by alpha has to be negative. Well, because alpha is positive, I can multiply it by alpha, and I see that fx plus alpha d must be less than f of x. Okay? So that's a way of formally proving that if this derivative f prime of 0, which is the dot product of the gradient of f at the point x and the descent direction, if that is negative, then my d is a descent direction. Okay, so let me write that clearly. If the gradient of f at x transpose d, if you wanted, I could also write the dx like that, the descent direction is computed at that point x, okay, but usually that's not necessary. So if this is negative, then we have just shown that in that case d is a descent direction. Now the proof, like many proofs in calculus, probably don't give you an intuition why is that the case. So let me give you an intuition. Let me on an example. Super simple example. Let's say that, I don't know, I keep writing the F. I guess I meant to write G everywhere. I'm sorry. Okay, imagine all the F's were G's. Okay, let me try to go back to G now. I usually write F for a function, right? But I only used F for forces, and that's why I kind of try to avoid it, but I can't. I always slip back. So here is an example. Let's see if I can get it right. So g of x and y will be just x plus y, okay? As simple as a function gets, okay? Obviously, it's a function from R2 to R, right? You can imagine what kind of height field it is. It's like a linear ramp, right? At 0, it's exactly 0, right? So let's look at the gradient of g. What is the gradient of g, by the way? It could be potential. Kind of the gravity potential is kind of similar to this, right? Actually, if you said that the gravity points in certain direction, you could say this is, yeah. But that doesn't matter, right? You can compute gradient of any function. It doesn't have to be potential function. Yep, the gradient is exactly 1, 1. right? The gradient are the partial derivatives, so partial by x is 1, partial by y is also 1, so this is really a vector 1, 1, okay? And if I plot it actually at any point, okay, because that's a linear function, so the gradient is the same at every point. If it was not a linear function, then the gradient could depend on where do I take it. Here it doesn't matter. Here the gradient is like this. It's 1, 1, okay? And if you imagine how this function, so where is the zero level set of this function? If this is my x and this is my y. Yes, exactly. You're showing the right thing. Let me try it in a fancy way. So let's see if I can do it in a fancy. The zero level set looks like this, okay? Now, if you wanted level set like, I don't know, 0.5 or something like this, then that would look like this, right? And so on. So now you have an idea how that function looks like. And you also probably know that the gradient points in the direction of steepest ascent of that function. Okay? So this is my gradient of g. And in that case, this condition, where I meant the f to be g, I apologize. So this will be g of x. What this condition means geometrically. Let's say I'm at the point 0, that at this point right here. Exactly. It can be any vector from this half space. Okay, so it can be this guy, it can be that guy, it can be this guy, it can be this guy, it can be this guy. Not exactly this one, right? Because then I will get exactly 0 in the dot product here, so that would not be good enough. It needs to be strictly less than 0, right? So this is just a dot product. It's a dot product between the gradient and the descent direction. This says that d is a descent direction if this dot product is negative. It means it has to point away from the steepest from the steepest ascent direction, which is the gradient. Okay? So given this discussion, you can probably tell me what would be the most obvious choice for descent direction, right? What would be the most... Exactly, yes. So d equals minus negative of the gradient is an obvious choice of a descent direction. This leads to a method which is called gradient descent, and you must have heard of that, if nothing else than like neural networks, right? Because that's the method that's used to train neural networks. Why is that always a descent direction? Well, that's obvious, right? Because if you do this with this, then and there is the minus is kind of important, don't forget the minus, then you get minus the squared Euclidean norm of g, right? And this is strictly less than 0 unless what? Unless the gradient is 0, right? But what does it mean that the gradient is 0? It means you are at a critical point, right? So you don't really have anywhere to go with the descent method. So, and that's also like one of the stopping criteria, which I erased. So if this is the case, you stop your iteration. You don't have anywhere to go. If this is not the case, then the steepest descent direction is always a valid descent direction, or the negative gradient direction is always a valid descent direction. All right, it's not always a great descent direction. Sometimes it is, sometimes it is not. And that's a complicated discussion that leads to, or more complicated discussion that leads to Newton's method. And I will leave it for the next time. But what I'd like to tell you today is how line search works. So that means we already have a descent direction. And now we solve the problem of line search, which means that we have already picked a descent direction. And now what we need to do, we need to find this alpha such that the fx plus alpha d will get as small as possible. Okay? So that really is this 1D optimization problem when we are here, right? This is my alpha. This would be like the phi of alpha function. We want to get as low as possible. If it's non-convex, by the way, then this function could also look like this, in which case it gets a little bit more annoying. But you can still think about it. How you can still try to solve it, right? solving it exactly, that would be sometimes called an exact line search. And actually, in some special cases, you can afford to do an exact line search. A typical case is conjugate gradients when this function is just quadratic. Yes, it's just quadratic. So it's actually not so hard to find an exact solution of the line search. If f was a polynomial, then you are also minimizing a polynomial in 1D, and then you can also do exactly, not so hard. Okay. But in most practical cases, you will just resort to inexact line search. Inexact line search, which basically means just give me alpha that's good enough. Doesn't necessarily have to minimize it. Just decrease the value of the function enough, and that's okay, because even if I did not optimize this perfectly, kind of doesn't matter, because then I'm doing another iteration, so I pick another descent direction, so I can fix that later. So it's kind of like only like a time trade-off. Okay? And that's where the hackery starts, and that's where the parameter tuning starts. Okay? And there is a zillion of line search methods. They are more hairy in the non-convex case. I will tell you the one that worked well for us, and that works fairly well, or pretty well, in solving these implicit integrators. Okay? And that is called backtracking line search. It's actually one of the easier line searches, which already is robust. Okay. So, and it assumes that alpha equal 1 is a good initial guess. So it's not ideal for gradient descent, but it works pretty well for Newton's method. And that's what we'll talk about the next time. But you can also use it just for gradient descent. So here is where the hackery starts. You have some parameters. So you have parameter rho between 0 and 1. And you also have to give it a parameter c between 0 and 1. And I'll explain what does that mean in a second. And you initialize it with alpha equal 1. That's your initial guess for the line search. If you have a more intelligent initial guess, feel free to use it instead. Okay? And then the algorithm looks like this. Until fx plus alpha d is below fx plus, and here is your step size parameter. Here is the tweaking parameter rho, and here is the dot product between the gradient and the descent direction. Okay? So until this is satisfied, what you're going to do, you are going to take alpha and multiply it by c. Okay? And you are going to repeat it until this inequality constraint is going to be satisfied. Okay? This inequality constraint has a name. It's called the Armijo condition. You can hear all sorts of funny names here. Sometimes you have Wolf conditions and strong Wolf conditions, and those are some of the more complicated line search algorithms out there. For the backtracking, we will just be happy with the Armijo condition. Okay. By the way, this is exactly what I had before as the derivative of the phi function, where the phi and that should work. Okay, so this is a visualization of what this constraint means. It depends on the parameter rho. Okay, that's your tweaking parameter. So this would be my alpha. This is the phi of alpha function, right? That's what we want to be minimizing. This is the f of x. That's for alpha equals 0. So if rho was 0, how would this constraint look like? If rho was 0, this would all drop out. You don't actually want the rho equals 0. I'll explain in a moment why. But if it was 0, then this would be just fx plus alpha d has to be less than f of x. Okay? So that means that if I draw this line here, it didn't work. So that just means that I'm looking for any value up to here, okay? Any of these values below this line would satisfy the inequality condition for rho equals 0, okay? So for rho equals 0, we would get this line, okay? Now, if rho was 1, then what we have here? Then we have here exactly the derivative at 0, in which case this line becomes the tangent, okay? So it looks like this, okay? So in a sense, so this corresponds to rho equal 1. Okay, this rho equals 0, that's too relaxed of a constraint. Okay, this would not have to give you sufficient reduction in f. It could just like go here, or it could just stay almost there, just like move a tiny amount. So your line search would actually not do enough progress. Okay, now if you give it rho equals 1, then it's like asking for too much, because you cannot possibly go below the tangent, right? Definitely not in the convex case. Okay. So the rho between 0 and 1, that corresponds to some line that looks like this. Okay, this would be, I don't know, rho equal 0.5 or something like this, or 0.3. That's the more usual value you would use. And that means that any x from here would be good enough. Okay, that's the idea of the Armijo condition. It's a blend between this overly relaxed version of the constraint and this impossibly hard. That's also why I excluded the 0 and 1. It needs to be something between, strictly between 0 and 1. Okay? But the most important trick here is actually this innocent looking line. Okay? This means multiplying the alpha every time by a constant c. Okay? And this constant c also needs to be between 0 and 1, okay? And that's really the main trick of the backtracking line search, because you do not know the scale, okay? You don't know if the alpha equals 1 is going to be good enough. It might be that you need to go to 10 to minus 3. It might be that you need to go to 10 to minus 6 to reduce the alpha, okay? So you need to do this kind of multiplicative exponential kind of search so that this works. Okay, so this is actually the more important thing than this. I mean, they're both important. So the usual values you would use, at least in convex optimization, would be that R would be between like 0.01 to like 0.3, and the C would typically be within like 0.1 to 0.8. Okay. The C is more intuitive to kind of tune, because if the C is like relatively high, like 0.8, that corresponds to pretty fine-grained search. Okay, you are gonna try lots of points here, right? If the C is 0.1, what does that mean, right? You try one, then you try 0.1, then you try 0.01, then you try 0.001, right? So you go to 0 really quickly. So that's very crude line search corresponding to C equals 0.1, okay? Unfortunately, there is no general answer. You have to really tweak it. That's where the hackery of these solvers starts. And unfortunately, it does not end there. There is more parameters you have to worry about. But that's currently the best thing we can do. In the convex cases, it's actually not super sensitive to these parameters. You can kind of set them to something. Because if you don't really get the best possible solution, it kind of doesn't matter, because there's going to be another iteration of the line search, right? So if you didn't do a great job, then the next iteration will fix it. And the Armijo condition is there to safeguard against insufficient progress, okay? If you just moved it a tiny amount, you would basically lose the opportunity to minimize that function. And you are already paying the cost for computing the descent directions. You have to do some compute to compute the descent direction. So it makes sense to also invest some effort into figuring out how far exactly in the descent direction you should move to get a good decrease. Okay? And that's, I guess, it for now. I think we'll stop here. What we'll talk about next is what are the good choices of the descent directions. And I'll tell you that the gradient descent is sometimes a good choice and sometimes it's a terrible choice, okay? And it turns out that in the problems in phys-based, usually it's the terrible choice, the gradient descent. And you need to do some more sophisticated techniques to find a good descent direction, such as Newton or quasi-Newton methods. And also you have to be careful to not crash or not return a nonsensical result if the objective is non-convex. So there are some precautions how to handle non-convexity. And we'll save this for not the next week because it's spring break, but the week after the following week. All right, sounds good. Any questions? All right, let's stop.